think Mr. James Stewart had a blast with this one, or whoever wrote this problem. This is the hardest partial fraction decomp problem that you will pretty much encounter. Pretty much. So if you can solve this, you're really good to go. This is problem 37 in the chapter. It really doesn't get much worse than this. And by worse, I mean more fun. It doesn't get much more fun than this. But we're going to walk through it, and then knowing the steps by walking through this problem is going to allow you to be able to solve any really partial fraction decomp problem like this. Keep track of your algebra. If you make one small algebra mistake, that'll get you. So what I do with this kind of denominator is treat x like x plus 0. That way, it just makes me feel like it's a standard fraction decomp problem. So we're going to write out everything like we normally would, right? So we start with a over x plus 0 plus b over, now, well, be careful, watch this. What's it over? X squared plus 1, right? Because this is squared, so we're going to end up building up to it. But, right, so let's just do that. Okay? Because that's what you do when you're doing this separate fractions. So what do we do with the numerators? Well, we knew how to set up the denominators. We knew how to set up the 3 different fractions. Just focus on the fact that this is a quadratic, right? And whereas this was x to the power of 1, so we just had a, this is x squared, so it's going to be bx plus c instead of just b. Because of that, we know that we're going to at least start with d here, a, b, c, d, and then this is also a quadratic, so be dx plus c. What am I talking about? I know the alphabet. Dx plus c. So this is the kind of wonky thing off the bat. 1, 2, 3, 4, 5. We have 5 variables, right? So it's like, holy smokes, we gotta find the values for these 5 variables before we can actually plug them into an integral and be able to integrate them. Yes, this is true, but there's gonna be a different trick here that we're gonna go about this problem that is a little bit different than every other partial fraction decomp problem, or most of them, I should say. So this, what do we normally do? Multiply by x squared plus 1 squared, okay? Multiply by the original denominator, right? And then that's gonna give us our it's going to give us our equation that we can set equal to the numerator, which will then allow us to find all 5 of these variables. So that's the same, right? So when we multiply this by this term, what happens? Well, the x plus 0, this is technically x plus 0. Here, I'll write that, make it more clear. This denominator is the same as this, okay? That's the same, right? Just adding 0. These cancel, x plus 0's cancel, and then it's just a times x squared plus 1 squared, okay? And then we have bx plus c as one term, and then what's canceling out the denominator? X squared plus 1, and then 1 of the x squared plus 1s, right? So we're just going to have the x plus 0 times x squared plus 1, but not squared because one of them canceled out, okay? Plus dx plus e, okay? Being multiplied by just x plus 0 because these x squared plus 1 squared got canceled out with x squared plus 1 squared, so that's gone. And now we just have x plus 0 being multiplied to that, okay? And that is, you guessed it, going to be set equal to our numerator, because that is what you do in these partial fraction decomp problems. So we have this. Okay, now whereas normally what we'd start doing now is try and find variables that that would equate to 0 in this equation, so that for certain variables, so that we can find specific variables, the values for them. Now, you can look and be like, okay, well maybe 0 would work, right? Because, well, 0 would cancel out this one, and then 0 would cancel out that one, and then we could find A. Okay, what about after that? Okay, when you have an equation like this, and you need to find the variables for all of them, what you can do is we're going to algebraically multiply this whole thing out, and then look at what coefficients for certain powers of x we have, and then we can relate that back to this original equation and find our values for A, B, C, D, and E through that strategy. Now, you can try and explain math through talking, but math is a separate language than English, right? And that's why you got to see it on the paper, or on the whiteboard, I should say. So I'm going to write this out, and you'll see the strategy here, okay? Whoa. So, algebraically solve this thing out. A times x squared plus 1 squared plus bx plus c x plus 0 x squared plus 1, okay, plus dx plus c x plus 0. That's going to be equal to 5x to the power of 4 plus 7x squared plus x plus 2. All right, 2 is pretty bad. So I just rewrote this whole equation, to be honest with you. Just rewrote the whole thing, because we're going to multiply everything out. So what does this actually end up looking like? Right, this is being multiplied by itself. Bx times x is bx squared. Bx times 0 is 0. Cx, c times 0 is 0. And then don't forget that there is this second term, or third term really, being multiplied. Now it's only the second term because I multiplied these out, and then this is still there. So I put that there. Plus dx times x is dx squared. Dx times 0 is 0 plus ex. Okay? E times 0 is 0. And that is still equal to the same numerator. Okay? We're really close. Ax to the power of 4 plus x squared plus x squared, so plus 2x squared plus 1. This is bx squared times x squared, bx to the power of 4 plus bx squared. Okay, bx squared times 1. Cx cubed, okay, cx times x squared plus cx. All right, plus dx squared plus ex equals 5x to the 4th plus 7x squared plus x plus 2. All right, so I algebraically just multiplied everything out, okay? Kind of, for the most part. Let me just actually distribute this A. That way things can be very clear. Okay, now, here's where the strategy lies, okay? What color do I want to use for this is the real question. Not really the real question, but it is a question that's going on in my mind. So, we're just going to go from the highest power down to the lowest power. What terms do we have for x to the power of 4? A, B, okay? That's it on this side. That is it on this side. So we're worried about this left-hand side. We're worried about the side that's actually in respect to all of our variables that we have. And so to the x to the power 4, we have a plus b. So we're going to factor that out like this. Okay? Right? Okay. So we factored the a and the b. Where is it? We factored the a and the b out of the x to the power 4. And those are the only x to the power 4 terms we have. Okay? So now let's look at the next best one. We have cx cubed. And that's about it. So we have cx. We have, c. Sorry about that. C for x cubed, right? Just factor the c out. So we're just factoring out what we have for that power. For the x squareds, though, we have 2a x squared. So we have 2a. This is for the x squareds. We have 2a plus b plus d. Ran out of room here. We have 2a plus b plus d, and I got that from this 2ax squared, factored out the 2a, bx squared, factored out the b, and then we had a dx squared, so I factored out that d. Okay? Now, what about x? For x, we had just c and e. So we factor those out. C plus e. Okay. Yep. So cx and ex. We factored those out. All right. I should be marking them off like that. We did that one and that one. We did the cx cubed. Now, for just like constant, we'll do c for constant. Constant, we just had a. Okay? Now, for the other side, we can just write those out as well. So we had 5, 0 for x cubed, we didn't have anything. 7, 1, and 2 for our constant. Okay? And you see where I got that? We have the 5x to the power 4. We had no term for x cubed, but we did have a 7x squared, and we did have a 1x, and we had a 2 constant. So what we're able to do now that we factored out all of our things for the certain powers is set them equal to the other side. And so what that looks like is a plus b equals 5. C equals 0. 2a plus b plus d equals 7. C plus e equals 1. And then a equals 2. Boom. We have system of equations now that we would have to solve, and I put it in quotation marks because that is what it is, but it's also like not it. We kind of lucked out with this because look, we already have 2 values that we got out of doing this strategy. So we have a equals 2 and c equals 0. So now what we can do is just find the other 3, and that's not too bad with these kind of equations we have, and I'll tell you why. Because we know we have these guys and these guys. So let's just plug them in down here and do something like, I don't know, 2 plus b equals 5. What's that going to give us? 5 minus 2 is 3. Okay? So we know that b equals 3. All right? And now if we do something like, I don't know, what can we do? C plus E equals 1. Okay, or C is 0. Well, what does E equal then? E equals 1. Okay. Well, now we just need to find D, because we have A, we have B, we have C, and we have E. We just need to find D. So let's grab that 2A. Let's just grab that 2A plus B plus D equals 7 and plug in our values. So we have 2 times 2 plus 3 plus D equals 7. 4 plus 3 is 7 plus D equals 7 minus 7 minus 7, D equals 0. Okay? Okay? Spectacular. So we have A equals 2, B equals 3, C equals 0, A, B, C, D equals 0, and E equals 1. Okay? Bam! All right, 1, 2, 3, 4, 5. We found our 5 variable values by doing this kind of method by looking at our powers of x and factoring out the coefficients for the powers of x. Okay, and then setting them equal, doing the same thing for the other side, setting them equal. If you look at the pink, that's what we did. Okay, and then we just solve for them. Cool. Now we got to do the integration. What's A? A is 2 over x plus 0 plus, what's B? 3. Right, so we're grabbing this. So B is 3 plus C is 0 over x squared plus 1, okay, plus D, which is 0, plus E, which is 1, over x squared plus 1 squared dx. All right. Spectacular. Excuse me. So let's make this into 3 different integrals, right? I'm just noticing, I'm just like seeing ahead how we're gonna need a lot of room here. So that's okay. 1 over x, because x plus 0, plus 3x plus 0 is just 3 times x over x squared plus 1. Okay, you guys see that? Just pull the 3 out. X plus 0 is just x. Don't forget your dx. Okay. 0x is just any 0. It doesn't matter what you plug in for x. Literally anything is multiplied by 0, right? So it's going to be 0. So we can get rid of that. And then we just have the integral of 1 over x squared plus 1 squared. Now, you guys might not be able to see this right away. We can do a u-sub for this. What is this? You can't u-sub that. If you want to try writing it out, go ahead. But you would try, you know, if you try doing the u equals x squared plus 1, take the derivative of u, you would get 2x, so 1/2 du equals x dx. Well, how is that going to help us? We don't have an x term, so that u-sub wouldn't work. And then it would only make it worse if you tried doing the whole thing squared, right? Can't do just x squared. So this is a trig substitution. This is going to be a trig sub. So we have a partial fraction decomposition problem to trig substitution integration problem. It doesn't get more delicious than this, people. This is literally peak. No, I mean, it does, but I mean, hey, I'm saying that, oh, geez, you put that there. This is going to be a blast. So, if you can see right away, yes, this is just 2 natural log of x. We can use sub this, I'll write that out, and then we'll start with the trig sub. Or should I just do the trig sub somewhere else? Okay, I'm going to do the trig sub with a new color. We were just starting the trig sub here. So, when it's x squared plus 1, that means we're going to use tangent. Okay? You can either look at your trig sub identity table or your trig sub table. You can either look at your trig sub table for that, or have it memorized. Derivative of x is secant squared theta in respect to theta. We took the derivative. Okay? So, let's go ahead and sub in that substitution that we did. So x is equal to tangent of theta. So plug that in for x, and it's squared because x is squared. So tangent of theta squared. That looks like that, and then that is also being squared. Okay. Now what is dx being subbed with? It's being subbed with dx equals secant squared theta d theta. Okay. This is a trig identity. Okay. This is tangent squared theta plus 1 equals secant squared theta. Okay? This is a trig identity. So knowing this, we can do a substitution with that trig identity of tangent squared theta plus 1, so that this becomes 1 over secant squared theta squared being multiplied by secant squared theta d theta. Okay? Now, secant squared theta times secant squared theta is going to get rid of 1. And if this is secant of theta to the power of 4, then 2 of those are going to go away. So it's just 1 over secant squared theta. Okay? That square just got put away because we had a secant squared theta. And this is technically this. And so this equals this. Okay? That's what happened there. And then that d theta stays. So, what we're going to want to do is another identity where we want this to be something different. What is 1 over secant? 1 over secant equals 1. 1 over secant is equal to cosine. Okay? 1 over secant of theta equals cosine of theta. So, we can write this as cosine squared theta, d theta. Okay? Cool. Now, to be able to integrate that, we still need to do a power reduction formula because we can't integrate it when it's to the power of 2. So, can we recall our power reduction formula? It is going to be cosine of squared theta equals 1/2 1 plus cosine 2 theta. This is your power reduction formula, okay? So we're going to use that. And that's what that's going to turn into. Now, this is why this problem is just kind of crazy, because it's one thing to go to a trig sub, but it's another thing to use this kind of trig sub where we're using so many different identities. So it really is something pretty special here in this problem. Now this 1/2 is going to distribute And so we're going to have 1/2 of 1 d theta plus 1/2 of cosine 2 theta d theta. So what I did was distribute the 1/2 plus 1/2 cosine 2 theta, and then split that up in two different integrals. So integral of 1/2 d theta, pulled it out in front, plus 1/2 times cosine of 2 theta d theta. Okay. This becomes 1/2 of theta when we integrate it. But this is going to be a u sub, okay? It's going to be a u sub. I'm afraid that yellow might be too bright. So this is going to be a u sub. Is this light blue? Could be good. We're going to use that. So u equals, you know what? For the u substitution, we're just going to use the same color here, actually. So this is going to be u equals cosine of 2 theta du equals, sorry, our u is just going to be 2 theta. I don't know what I'm thinking. 2 theta du is going to be 2 d theta, okay? And then 1/2 du equals d theta. So now we have 1/2 theta. Oh, here, let's finish this u sub. So then it's going to be the 1/2 pulled out in front, cosine of u du, because we pull the 1/2 out in front, okay? And when we integrate that, it's just going to be 1/2 sine of u, which is 2 theta, and then 1/2 theta plus that, okay? Sign identity. We have another one, as if the sign identities that we've all used so far weren't enough. So this is going to become, so sine of 2 theta equals 2 sine of theta cosine theta. Okay? This is the trig identity that we're going to use for that. So this is going to become 1/2 theta plus 1/2 times 2. Oh, notice how that 1/2 multiplies? This 1/2 in front of this integral, after we integrated it, is going to multiply to the 1/2 that came out of the u substitution. So this becomes 1/4. Okay? 1/4. 2 sine of theta cosine of theta. All right. So, now that we have that, we get to draw a triangle. Now, I like to draw the triangle for these problems to understand what's going on. If we have a 90-degree angle, so we had we had x equals tangent when we started with, right? And tangent is opposite over adjacent, right? Well, this is x over 1, so your opposite is x to theta, and then your adjacent is 1 to theta. And then if you wanted to find what your hypotenuse is, Pythagorean theorem says that x squared plus 1 squared equals c squared. Square root that, and that equals your hypotenuse. Okay? All right. Now that we have that information, we need to understand how we can sub that in for sine and cosine. So what we got to do is just know that sine is equal to that sine of theta is equal to opposite over hypotenuse, which is equal to, what's our opposite? It's x. And our hypotenuse is x squared plus 1. Okay? Our cosine of theta is equal to adjacent over hypotenuse, and that is, our adjacent is 1, and our hypotenuse is the same, right? X squared plus 1. So now that we know that, we just have to convert, we figured out how to get sine and cosine of theta into these. We just got to figure out how to convert 1/2 theta. And to do that, just grab the x equals tangent again. And the x equals tangent of theta, if you want to get that for x, then you just do the inverse tangent, so arctan of x equals theta. And then now we can plug that in for that. Okay? So what this really ends up giving us is this ends up giving us 1/2 theta plus, bring that 2 out, so it's 2 over 4, so 1/2, our sine ended up being x over the square root of x squared plus 1. And then our cosine ended up being 1 over the square root of x squared plus 1. That's how we got, that's how you solve for that integral, okay? So, coming back up to this integral, we know that that's just, if you want to do the u sub out for that, actually no, this doesn't even have to be u sub. What's the antiderivative of 1 over x? It's going to be natural log of x. So we know that that's 2 natural log of x. If we wanted to write out the u sub for this, this is 2x squared plus 1 du equals 2x, okay? This is in respect to x, 1/2 du equals x dx, and there is an x on top, so this works out pretty well. So this is going to be 3 times the integral of 1/2 du, pull that 1/2 out in front, over u, right? And this is the same as 1 over u du, so it's going to be a natural log. So we can do 2 natural log of x plus 3 over 2. We have 2 natural log of x plus 3 over 2 natural log of u, right? Because it's 1 over u. And so u is x squared plus 1. And then we have plus 1/2 theta. Oh, I was being silly here. We rewrote it on for a reason. So 1/2 tangent, negative 1 of, inverse tangent of x. So plus 1/2 inverse tangent of x plus 1/2 x over square root of x squared plus 1 multiplied by 1 over the square root of x squared plus 1. And that's a general antiderivative, right? So plus c. All right. There you go. There is your answer.